Picture this. It's the 1920s, and you've got a toy dog named Radio Rex. Now, Rex is actually one of the very first speech recognition machines ever built. As a kid, you'd just call out his name, and a little spring mechanism would launch him right out of his wooden house. It felt like absolute magic, right? But it wasn't. Rex's release spring was precisely tuned to trigger only when it caught 500 hertz of acoustic energy, which just so happens to be roughly the first formant of the vowel sound in the word Rex, so the dog seemed to magically come when called. It's a brilliant, purely mechanical solution to a massive challenge we are still totally obsessed with today.
Welcome to The Explainer. Today, we're popping the hood on automatic speech recognition, or ASR, and decoding exactly how machines take messy, chaotic sound waves and magically turn them into crisp, readable text. Obviously, we've come a long, long way since spring-loaded toys. Today, speech is our natural interface for everything from smartphones to complex digital assistants. But teaching a machine to truly hear us, that involves some incredibly elegant computer science.
So, here's our roadmap for today. We'll start with the speech recognition challenge, then look at why speech is hard, move into slicing sound with CNNs, translating sound with encoder-decoders, and finally, wrap up with self-supervised speech and Hubert. Let's get right into it.
Part 1. The Speech Recognition Challenge.
Think back to 1851. The poet Thomas Lovell Beddoes wrote about the wordy wavelets of your voice. It's a beautiful image, right? Now, contrast that fluid, poetic idea with the clunky, rigid, mechanical engineering of the Radio Rex toy we just talked about. That contrast perfectly highlights this desperate, centuries-old human obsession with capturing something as completely ephemeral and fleeting as the human voice.
And that brings us to the core challenge of ASR. How do we take these jagged, messy, acoustic waveforms and map them directly into exact text? Like taking a random audio spike and mathematically proving it translates to, "It's time for lunch." This isn't just a cool tech trick for convenience, it's an absolutely vital tool for accessibility. Historically, brilliant folks like the blind poet John Milton or the novelist Henry James had to rely entirely on human dictation to capture their work. Modern ASR provides that exact same lifeline, but it does it automatically.
Which leads us to part 2. Why is speech actually so hard for a machine to figure out?
Well, it really comes down to 4 massive dimensions of variation in how we talk. First up, vocabulary size. Building a simple yes or no system is a piece of cake, but natural conversation uses over 60,000 words. Second, the audience. When we talk to a machine or read an audiobook, we unconsciously slow down. We over-enunciate. But human-to-human speech, it's incredibly fast, people talk over each other, it's a mess. Third is channel and noise. Parsing audio from someone reading a book in a totally silent studio is a breeze for an AI, but try a distant microphone on a noisy city street, absolute nightmare. And fourth, accent and speaker class. If your system is only trained on a standard, neutral dialect, it's going to completely fall apart when it encounters regional variations, diverse ethnic dialects, or, the chaotic speech patterns of toddlers.
To put that into perspective, just look at the raw data on word error rates, or WER. A pristine audiobook recording, you're looking at a tiny 1.4% error rate. Almost perfect. But jump down to the Chime 6 dataset, which is basically a chaotic 4-person dinner party recorded on distant mics, and suddenly that error rate skyrockets to an agonizing 25.5%. Context, background noise, and conversational speed literally change the whole game.
All right, part 3, slicing sound with CNNs.
To really grasp how convolutional neural networks, or CNNs, process speech, we need to quickly nail down 2 essential terms, kernel and stride. A kernel is essentially a tiny mathematical network, a little vector of weights that hunts for very specific patterns in the data. And the stride? That's just how much the kernel moves over the input between each step. So if you've got a stride of 2, you're basically skipping every other frame, which chops your data length right in half.
Think of this kernel as a sliding magnifying glass. If it has a width of 3, it's analyzing 3 frames of audio simultaneously by computing what we call a dot product. Now, in modern systems, a single frame is usually about a 25 millisecond chunk of speech. So you've got this mathematical magnifying glass sliding across the timeline of the sound wave, pulling out crucial phonetic clues, things like format transitions or the tiny fraction of a second lip closures right before you make a P or B sound.
Now, let's zoom out for a second to see the bigger picture. The audio actually gets converted into log-mel spectra to split it into specific frequency channels. And these kernels? They are stacked.
They're pulling information from up to 128 different input channels all at the exact same time. The system combines this to build these incredibly deep, complex, latent representations of the sound, often projecting it into over 1,000 different mathematical dimensions. This right here is the rock-solid foundation for actual text translation.
Moving on to part 4, translating sound, encoder-decoders.
So why do we bother compressing the signal so heavily with those CNNs in the first place? It's because of a really stark mathematical mismatch. Your average spoken English word drags on for about 25 frames of audio, but that exact same word averages just 1.3 text tokens. If you try mapping 25 frames directly to a single token, you completely overwhelm the system. The CNNs do the heavy lifting of shrinking that audio sequence down so the next stage can actually handle it without crashing.
And that brings us to the real heavy hitters, state-of-the-art architectures like OpenAI's Whisper. Whisper takes that highly compressed sequence of audio vectors and feeds it straight into an encoder. The encoder's job is to fully map out the acoustic reality of what was just said. Once it has that, it passes the baton over to a decoder, which acts a lot like a super-tuned language model. The decoder takes that acoustic map and gets to work generating the final texts, token by token, letter by letter. But the absolute genius of this setup is how those two halves talk to each other. The cross-attention layer inside the decoder block is really the secret sauce here. It allows the text-generating decoder to constantly look backward and attend to the original acoustic input held over in the encoder. So as it's trying to predict the very next letter of the transcript, it's constantly double-checking the acoustic memory to make sure the text matches the actual spoken sounds. It's literally like a live translator constantly glancing back at their raw audio notes before writing down the next word.
Finally, part 5, self-supervised speech, Hubert.
We've officially entered a total paradigm shift with self-supervised learning, or SSL. Older models were absolutely desperate for massive, meticulously paired data sets of audio and human-written text transcripts. But self-supervised models, they learn directly from raw, messy, unlabeled sound. Think about how a human baby learns to talk. They don't sit there reading a transcript while you speak to them, right? They just listen to the world around them, pick up on patterns, and categorize sounds organically over time. SSL models are essentially trying to mimic that exact same biological process.
The Hubert model actually pulls this off using a really clever 4-step process. First, it extracts basic acoustic features from just mountains of unlabeled audio. Second, it clusters those sounds into discrete phonetic units. It's basically inventing its very own internal alphabet. Third, it intentionally hides or masks chunks of its own audio input. And finally, it plays a massive guessing game with itself. It trains by trying to predict exactly which of those invented phonetic units belong in the blank spaces, just based on the surrounding context. By forcing itself to guess the missing pieces, it learns the deep underlying structure of human language without ever laying eyes on a single written word.
So as we wrap up this explainer, I want to leave you with a pretty profound question to think about. We kicked things off today with a mechanical toy dog from the 1920s that jumped at a single frequency. Today, we're looking at AI that invents its own alphabet and masters the intricacies of language just by listening to hours of raw, untranscribed human dialogue. If our machines can now truly understand us simply by absorbing the raw noise of the world, completely bypassing the need for written text, what kind of seamless, invisible interfaces are we going to build next? Those wordy wavelets of our voice aren't just shadows anymore. They are quite literally the foundation of our digital future. Thanks so much for learning with me today, and I'll catch you next time.